Welcome to ELET B70 Mechanical Systems. This is your professor, Roy Allard. This lecture is on clutches and brakes. Now, you may be wondering why clutches and brakes are in the same lecture. Well, clutches and brakes function in exactly the same manner. With a clutch, one shaft is spinning, and then we engage the other shaft to spin. So they both become one and they're both turning. With a brake, something is spinning, let's say our car wheel, and as we apply the brake, we're going to make those two as one. But since the brake mechanism is not rotating, it is affixed to the car's chassis, the wheel comes to a stop when the brake fully engages and becomes one. So you can see whether it's a clutch fully engaging and becoming one spinning motion, or a brake fully engaging and becoming one stopped motion, they work in a very similar manner. So we'll be talking about clutches, both positive contact and friction, radial and axial friction clutches, fluid clutches, electromagnetic, overrunning clutches, and then clutch maintenance and troubleshooting. These are positive contact clutches. So they don't allow any slippage, hence the name positive contact. When this square jaw goes into this like a square jaw coupling, those two shafts are coupled and they become like one solid shaft. There's no way it can slip if it's fully engaged. This spiral jaw coupling, well, it can be engaged because of the slant at a very slow speed, and the jaws go in here and make contact, so it is also, once it's fully engaged, a positive contact clutch. When it is, those two shafts are like one. Note this third statement here. Most positive drive clutches need to be engaged when equipment is stopped. Certainly at this point it would need to be stopped or running very slow, and then this is the cam. We would move this cam, there would be some linkage to a lever to it, and at exactly the right moment, if it was spinning slowly, insert the jaws together. So this is a square jaw with a square protrusion that is going to fit in this jaw opening. The square jaw clutch was one of the earliest positive drive clutches, and then the spiral jaw came later. Friction clutches and brakes have been around for years and years, way before modern America and the automobile was created. We had friction clutches and brakes. Before we get into the different types, we need to talk about the effectiveness of a clutch or a brake. So when we're talking about clutches, we're also talking about brakes. When we talk about brakes, we're also talking about clutches. Now, a clutch and a brake, although they work the same way, they're meant to do different things. One, they both are meant to tie both shafts together, but a brake ties them together and stops the rotation. A clutch ties them together and makes both of the shafts rotate as one. So the effectiveness of the clutch and or brake depends on three main factors. First is the coefficient of friction of the mating materials. What is the clutch or brake made out of? The surface area and the amount of force. We're going to look at these three items on the next few slides. First is a coefficient of friction. So friction is the force that resists movement. So the coefficient of friction is the force pressing the objects together divided by the force that resists the sliding. A larger coefficient of friction equals more resistance to movement and better braking. We could also put better clutch engagement here. So if we're going to have a larger coefficient of friction, we have to have more force pressing the objects together by a smaller force that resists the sliding. Now remember, friction is going to generate heat, and heat needs to be dissipated. That is very important in both clutches and brakes. If a clutch or a brake system overheats, then they become very ineffective. Second is a surface area. This is pretty simple. The more surface area of the mating areas of the clutch or the brake, the effectiveness will be increased. So surface area and effectiveness are proportional. For example, we take a disc brake rotor and a disc brake pad. There's actually two pads with a rotor, one on each side, and they squeeze the moving rotor. Those brake pads are held in what's called a brake caliper, and that brake caliper is not spinning when the car is in motion. It stays stationary. Most new cars, you can see the disc brakes through the wheels, especially on a sports car with some nice alloy rims. So when you're pulled up next to one of those, watch and look at the brake caliper. And you'll see it doesn't rotate with the wheel. The wheel rotates around the brake caliper. Or actually, the rotor is rotating inside the brake caliper, but then the wheel is mounted to the hub, which is rotating on the rotor itself. So if we take and want more effectiveness for a braking system, we have to make the surface area of our rotor larger and the surface area of the pads larger. So we can make them a little taller and put taller and wider pads. If we double the area that is pressing the pads and the rotor together, if we double that surface area of the pads and rotors, then we're gonna double our braking effectiveness. So this is why you see larger wheels and tires on larger cars to enable a larger braking system, the rotor, caliper, and pads, because the car is larger, which means it weighs more. So it has a lot more weight, which is the bottom part resisting that movement or the braking of the coefficient of friction. So that number is now becoming larger, so we have to increase the surface area because we need more stopping power. The same would work in a clutch, and we'll be showing you how to increase surface area in a clutch. Certainly we can make it larger, but there are some other ways to increase that area. Third on the list for effectiveness is the amount of force used. The greater the holding force that holds the sliding faces together, the greater the effectiveness. So when we use power brakes or a power clutch, it increases the amount of force used. Remember in the gear lecture when we looked at power steering? So we used the hydraulic pump and reservoir to help move that rack back and forth with a hydraulic piston. Well, power brakes are similar in the fact that we're not just pressing the brake pedal, which is forcing the brake fluid to push out the calipers, we're actually actuating a pressurized system, and it even gets much more complicated than that with the new ABS braking system or automatic brake system. Those actually have sensors on the brakes that are looking at each individual wheel's rotation, and it makes sure if one wheel is turning that the other wheel is not stopped. Because if that wheel is stopped while the car is still in motion, then we're in a sliding or a skidding action. So ABS is all computer operated with a special master cylinder that is controlling the amount of hydraulic fluid pushing the pistons out to stop the car, to engage the brake pads against the rotors or the brake shoes against the drum. So the more force, the greater the effectiveness. Now in a clutch, we also have to have force, and we'll be looking at that. But before we get deep into clutches and brakes, we need to talk about the two main types, radial and axial. We've heard radial and axial in many lectures prior to this, and so you probably understand what it means, but I'm going to show you and educate you to fully understand what it means when talking about brakes and clutches. So first we're going to look at radial friction clutches and brakes. So radial means the contact pressure is applied to the peripheral of a drum or a rim. Look at the wagon wheel example right here. You can see we have a brake. We have a block attached to a long lever that is going all the way up to that front stagecoach seat. With a small amount of force pulling back on that lever based on the pivot point of the fulcrum. Remember, go back to the basics of simple machines. We can apply a lot of force on this braking system. So as we pull the handle way up here where we're sitting, we have leverage that is going to force this block against the wooden wagon wheel. Now, to be a little more effective, that block could have some leather on it. So we're making sure the leather actually conforms to the whole wagon wheel. So when we pull it, we're going to stop it. But we're actually forcing this wheel radially. Here would be the center of the hub, and we're pushing it along the wheel or perpendicular to the axle. And this also would be a centrifugal clutch right here. And this is also a radial clutch. So a radial brake and a radial clutch. We'll look at this further on the next slide. So just like the name centrifugal clutch, it uses centrifugal force to actually open and close and activate and deactivate the clutch. So normally this is going to be on a drive shaft, such as, let's talk about a go-kart clutch. Most of you might have had a go-kart when you were a kid, or you've driven a go-kart, or maybe you've been to John's Incredible Pizza and have used those carts. Well, the electric ones are a little bit different because they're using DC power to a DC motor. But if you went to a karting experience that used gasoline engines or out at Camelot, those are going to have centrifugal clutches. If you've ever driven the cars at Autopia at Disneyland, those have centrifugal clutches. We don't have to engage a clutch. We don't have a transmission other than the two different size sprockets. And we just press on the gas, which increases the RPM of the engine and the RPM of the clutch, which allows the clutch to engage, and then we are able to move. So this is tied to the crankshaft of the engine. on like a lawnmower type engine or a Briggs & Stratton or a Honda, something with some pretty good horsepower, 5 horsepower or more. And this is spinning when the engine is running. But when the engine is running at an idle, this is not engaged. Now here is the two pieces separated. So this hub, which looks like this on the outside, this is for cooling. Remember, we have to get rid of that waste heat when the clutch is engaging. And once it's fully engaged, we don't have the heat. It's going from a non-engaged state to a fully engaged state where we're slipping, that we actually have some heat generated. So this is spinning with the motor. As the RPMs increase, you can see these springs here are holding this clutch pad. And we have 3 clutch pads around the circumference, and you can see they have some depth to them. Here's the springs. You can see one of them. And as the RPMs increase, these pads overcome the spring tension and they push outwards. So when they push outwards, they hit on the inside of this hub, and then the two pieces become one spinning motion. So this would be on the drive shaft or the crankshaft of the engine, and this whole piece right here would constantly spin when the engine is running. When the revolutions per minute, the RPM of the engine is great enough, then these clutch pads move outward. When they move outward, they engage the inside of the hubs, and now both pieces are spinning as one. Well, you can see the hub under here and over in here where we actually have a sprocket on it. That's a small sprocket, so it would be going to a chain to the drive axle that is larger. So we actually have a speed reducer. So this small sprocket is going to spin many times to turn our drive axle. We need that major speed reduction so we can have a torque increaser. I know it's been a few weeks since you watched that lecture. This is on chain drives. So if this isn't clear on the RPM and torque increasing and decreasing, go back and look at the chain drive video lecture again. So I'm going to show you an animation of a centrifugal clutch. Even though I explained it on the slide, I want you to see it in action. Sometimes visualizing it, if you really don't understand the workings of a centrifugal clutch, helps to realize what's happening. So the clutch is turning around, and the green parts are the centrifugal clutch parts. This outer part is what I called the hub. And as it started picking up speed, the weights overcame the spring tension, and the clutch was able to expand. So I'm going to show it one more time. So watch those green clutch pads right here. And you can see the centrifugal force push those pads outward. And then watch when the center part slows down, so the green shaft is spinning along with the other one, and then it releases. And that's how centrifugal clutch works. Now let's talk about axial friction clutches and brake. So in axial, the contact pressure is applied perpendicular to the rotating shaft. Different types are disc, multiple disc, and cone. So let's look at this. So this is in line. So here's our shaft. The shaft would be going through here, this thin line through all these pieces. Now I actually have a clutch pressure plate and what's called a clutch disc or a friction disc that I can show you during lab. But I want to explain how the clutch works on a manual transmission automobile. And then you can understand how just about any clutch works. that is an axial type. You should already know how a centrifugal clutch works. So in this case, we have a flywheel. The flywheel is bolted to the crankshaft. So it's bolted in here to the crankshaft. It has a hole in the center of it because the input shaft to the transmission has to go through these pieces. Now, if you watched on gear drives, you watched those videos on the manual transmission that I recommended you watch in that week's video section, then you'll see what the input shaft is. And it has splines on it which mate up to the clutch disc spline inside here. But the shaft has to go through the disc a little bit, so it goes inside the flywheel just maybe a small amount. So the flywheel is bolted to the crankshaft of the engine. Then we have a clutch disc. I'm so used to calling this a friction disc, and a pressure plate. So these are the two pieces I can show you in lab. Now, all these fingers here are spring tension forcing this disc, and this is a finished surface like a brake rotor. And this on the clutch disc is another finished surface. So we have material here where the clutch disc is going to mate, and then the same material on the back of the clutch disc where the flywheel is going to mate. So we bolt all this together, and we use a pilot tool or an old input shaft to a transmission to line everything up, and we can just stick it through the pressure plate and the clutch disc sitting just inside the flywheel. Then we bolt, you can see these holes out here on the flywheel, then we bolt the pressure plate up to the flywheel with the disc in between. So when the clutch pedal is not pushed, these two items will all spin at once. Actually, the three items, because the friction disc will spin as well. Because the clutch is normally, on an automobile, in an engaged state. So again, in a manual transmission, if the clutch pedal is not pushed, then the clutch is engaged. And you can tell this by if your engine's not running and you have your car in gear, try pushing your car. You can't, because you'd have to overcome the compression of the motor because the wheels are tied to the differential, which is tied to the transmission, and the transmission is tied through the clutch, which is engaged to the crankshaft. So we would have to turn the whole engine while we push this car. And that's why we can turn the engine by push starting a car. When we push in the clutch or put the car in neutral, then we can push the car. Then we just put it in gear or let out the clutch, and the spinning motion of this friction disc, when we push the car in gear, this is going to spin when we push our clutch in. When we push our clutch pedal in, it presses against these fingers, and it releases pressure on this disc pressing against the flywheel with the friction disc in between. So now the friction disc is able to freely spin as we push the car. As soon as we let the clutch pedal out, the friction disc and the flywheel and the pressure plate become one spinning motion or one spinning mass, and it starts to turn over the engine. Now, if the engine will start because of fuel and ignition, then the engine actually starts running, and then we can push the clutch in, put our brakes on, stop the car, and then we're ready to bring our passengers in, whoever was helping us push, and then we can take off. A lot of times the car is started like this when it has a dead battery, because the ignition system alone, once things are moving, will normally give enough voltage to start the car. So that's how a clutch works. So normally when we're driving, all three pieces are engaged and all three pieces are spinning, turning the input shaft to the transmission. So when we shift gears, we put in the clutch pedal, push it in, and then this friction disc is floating between these two mated surfaces, the flywheel and the pressure plate, and then we shift our gear, let the clutch pedal back out, and now everything is working or turning as one. So remember when we talked about increasing the surface area as one of the 3 factors for effectiveness? Well, here's a way we do that. We still have one pressure plate and one flywheel, and we have these teeth on the flywheel. That may be something that I should mention. Do you know what those teeth are for? Well, you're right. That's where the starter motor engages the flywheel when you turn your ignition on. That's what starts the car. You're actually turning the flywheel. And the flywheel turns the engine over. So we have multiple discs. We have 2 discs, so we've just doubled our surface area. Now it takes up a slight bit amount of space in here, but we have double the surface area because we have 2 discs with surfaces on both sides. So we actually have a pressure plate here mounted on here. This is just showing it separate. And then we have another plate in between. Well, the bolts are going to go through this plate and this plate through the flywheel. So whenever the engine is running, we're going to have the flywheel spinning, this machine surface spinning, and this pressure plate with the machine surface spinning. Then if this clutch is engaged, these 2 discs will spin. So the input shaft to the transmission will go all the way through both friction discs and just stick right into the flywheel. So the pilot shaft or the input shaft to the transmission doesn't spline into the flywheel in any way. It just has to go through a little bit to make sure it mates all the way through the splines of the clutch disc. So we've just doubled our surface area, so we've just doubled the effectiveness of this clutch. So a clutch like this would be in high performance vehicles or race cars. Now another axial clutch or brake mechanism, you can see we have this engagement handle, and this cone will fit inside this drum. So if this is spinning, then when we fully engage it, both pieces will spin. Or if this is spinning and we're activating it as a brake, when we pull this lever, if this piece here, this cone, is held stationary, then this spinning will actually come to a stop. So this could be used depending on how the mounting is for a clutch or a brake. The brake on your automobile, if it is a disc type brake, is also an axial brake or clutch. In this case, it's a brake because this caliper, this whole piece is called a caliper, is bolted through to part of the vehicle that does not spin around with the wheel. So what is happening here is that we have a stationary caliper bolted to part of the automobile chassis, and then we have pads inside this caliper that are removable, and I have a caliper, pads, and rotor that I can show you during lab. And we have hydraulic hose that is coming in here with hydraulic fluid, and it's pressing against this caliper. There's a piston in here that is pushing out, and it squeezes the pads against this moving rotor. Or maybe it's not moving and we're just stopped at a stoplight and we press our brakes. Because if we have an automatic transmission, if we let our brakes off and we're in drive, the car may start to inch forward. So when we press on the brake pedal, the piston pushes out and forces these brake pads in contact with the brake rotor surface. If this brake rotor surface is spinning, then it will come to a stop. And that's how disc brakes operate. They're basically pretty simple. We're just squeezing. It's like pinching that rotor. Have you ever had a bicycle with brakes? Even not disc brakes, but the two pads with those calipers. And when we squeeze the handle, those two pads hit against the rim. There's a picture of such on the first opening slide of this presentation. So we're just pinching that rim of the wheel to bring it to a stop. Or sometimes not pinching it really hard, just to slow it down a little bit to decrease our speed. Well, we can do the same thing with disc brakes. We're just pinching this rotating rotor, and our wheel is bolted to this hub mechanism, which is also our rotor, so it slows down or comes to a stop. Next, we're going to talk about a different type of clutch, a fluid clutch. So what's happening in a fluid clutch is we have a rotating impeller imparting energy by centrifugal force to a viscous fluid. So this would be our automatic transmission fluid. And this would be a torque converter. Here's a picture of one in an automobile. So we have to have some type of a clutch in an automatic transmission, but it's an automatic type clutch. So we don't have a clutch pedal when we have a fluid clutch. So the fluid is going to impart its motion to a runner attached to the output shaft. So what's happening, and I have a torque converter in the lab that I'll show you along with some of the other items I talked about in this presentation. And it's using hydraulic fluid as the clutch is spinning faster, and this torque converter is on the input to the transmission connected between the drive shaft, or excuse me, the crankshaft of the engine inside the bell housing of the transmission and the transmission. So it's part of the transmission, but it's an actual separate piece, the torque converter. And as the motion increases, the torque converter locks up to where it's spinning in one solid motion. So the crankshaft spins one end of the torque converter, and then the other inside part of the torque converter is going to be connected and will spin the input shaft to the automatic transmission. Another type of clutch and braking system is by the use of an electromagnet. We send voltage and current through the electromagnetic windings, and it engages the brake or the clutch. Here you can see one broken down, and you can see the electrical coil here, and it is going to pull this friction disc towards it, so it will either break or it will either engage the clutch, so both pieces will actually spin. This is what it looks like all put together. So it'll have a shaft on both ends, just like this one, and with the electricity, it will either tie both of those together, so that acts like a clutch, or if the other shaft in here, or the other part of this, and this is fixed through these bolts, it will bring this shaft to a stop. So it can be used as a brake or a clutch, depending on the configuration. Be sure to watch the video on electromagnetic brake and clutch in the video section of this week's lecture. This will have electromagnetic brake similar to this one, and it will show you how it works to engage both the shafts to stop it and brake it, or to be used as a clutch. Next, we're going to look at a magnetic trailer brake. So this trailer brake is very similar to the drum brakes on a vehicle. Now, most vehicles have disc brakes with rotors and brake pads, where a drum brake is going to have shoes on both sides. So there's two shoes or a set of shoes, and then a drum will go over the shoes. So I actually have a brake drum that I'll show you at lab when you're in class so you can see what it looks like. So what happens normally is you have a hydraulic piston in here from the caliper, and when we press on the brake pedal of our car, it pushes each shoe outward. So it would push this shoe towards the drum on this side and this shoe towards the drum on the other side, and the spinning drum will then come to a stop. All this mechanism is mounted to the frame or axle of your vehicle, but it doesn't spin with the axle or the wheel and tire. Just the outside hub spins to the wheel and tire. So the back side of the surface of the drum is actually finished similar to like a flywheel or a friction disc. So it's nice and smooth. And this is, the yellow piece here is an electromagnet. So you can see the wires going out through the brake assembly. And those would be connected to a brake controller in the tow vehicle. When the tow vehicle brake is applied, it sends voltage and current to energize this electromagnet. This electromagnet sticks towards the drum, and as the drum is spinning around in this direction, it pulls this red lever to the left. So this lever, when the electromagnetic turns on, this magnet wants to just spin around on the inside of that drum, the back side of the drum, but it can't because it's connected to the lever. So what happens is this magnet and brake move slightly this direction, and it moves these brake pads and pushes this one to this side and the top of this one to this side. This down here is just an adjustment. So this isn't doing anything to apply the brakes, it's just adjusting them. So when the magnet moves, we have a clearance that becomes closed, and these pads rub along the inside of the brake drum. And that's how an electric trailer brake works. Just a simple electromagnet that is moving a lever, and the lever moves the brake pads to both sides to hit amongst the drum or on the inside edges of the rotating brake drum. Normally, if you have a large trailer with 4 wheels with 2 axles, you'll actually have one of these brake assemblies on every single wheel. So you'll have 4 brakes on both of those axles, 2 on each axle, for a total of 4 brakes for every wheel that is spinning on the road. And it really, really helps, especially when you have a heavy trailer, to slow down that tow vehicle and the trailer. The next thing we're looking at is an overrunning clutch. So an overrunning clutch is a device that only allows rotation and torque in one direction, and then it can overrun in the opposite direction. So let's look at this. Here's our driver down here, and I want to say it's similar to a ratchet with a socket wrench. So here is our driver. It is spinning this way. And as it spins this way, these 3 balls get caught in here, and it moves the driven. Now, if we were to spin the driver in the opposite direction, well, then these balls would make clearance. They'd sit down here where there's plenty of clearance, and the driver would be spinning, but the driven would not, because there's nothing engaging this driven piece of the overrunning clutch. So we'll talk about indexing, overrunning, and backstopping on additional slides, but you can see if we started this driver and got the driver and the driven spinning in this direction and then stopped the driver, the driven would continue to spin because these balls would be back down here and it could just freewheel. Very similar to a hub on a bicycle. And here's what they look like. These different pictures. They really look like a bearing and can be often mistaken for a bearing. This is what the inside of one looks like. And this, of course, was just an illustration, and you can certainly see how these balls wouldn't grip unless we spin it in a clockwise position. When we spin it the opposite, it's not going to turn the driven shaft. So that's how this statement is true. It only allows rotation and torque in one direction. If we spin the driver the opposite, nothing's going to happen. The driver's spinning backwards, but the driven part is not moving at all. I already explained overrunning, but the definition is where the driven device can spin faster than the driver. So you could see that in that illustration. Once we stop the driver, the driven can keep spinning. So it will spin faster because the driver stopped. Or let's say we slow the driver down. Let me take you back to that illustration. So if we just slow this driver down and there's enough inertia in the driven part of the machine, it will keep spinning at the same rate and it'll begin to slow over time, but it will be going faster than the driver. So it allows that to happen. So let's say we turn off this motor and it goes from 1800 RPM down to 0. The machine will continue to spin and come to a stop on its own. The next item an overrunning clutch is used for is called indexing. Indexing is where reciprocating motion is transformed to an intermittent rotating motion. So think of a ratchet. Your arm just moves back and forth when you're using a socket and a ratchet. When you're moving back and forth, it will rotate when you pull the wrench towards you, the socket handle towards you, it'll rotate. When you push it back, it doesn't rotate. And then you pull down again and it rotates. So this is reciprocating motion, your arm moving back and forth, and it is transformed to intermittent rotating motion. So that's what an overrunning clutch does when it's used for indexing. Let's say this driver and we had a lever over here on it. Let's take one of these lines and we had a lever and we pull this down. Every time we pull it down, it's going to cause these balls to engage and the driven to move. Then when we let it go back up, the driven will spin and then slow down to a stop. But if we keep pulling the lever down, okay, on this imaginary lever on this line from the driver, then it will move. So this is linear motion and will create an intermittent driven or circular rotational motion. Indexing. The next item that an overrunning clutch is used for is backstopping. So it's meant to prevent any rotation in the reverse direction. So for example, a backstopping, the driver is held stationary. The driven, as it starts to rotate backwards, it's going to bind in here with the driver and these balls, and it won't be able to be spinned counterclockwise. So that's backstopping. It'll turn a little bit backwards and then come to a halt. It won't even make hardly any revolution because you can see this ball will get caught in this space. And with the driver stopped, the driven won't be able to rotate backwards. So an overrunning clutch can overrun, index, and backstop. Next is clutch maintenance and troubleshooting. You always want to refer to the manufacturer's equipment manual for specific maintenance guidelines. Every clutch and brake may be slightly different, but if you're working on automobile brakes and you are working on the same type, well, they'll be very similar, but some specifications might be different. Always use the exact parts that are meant to be used inside of a clutch or in a brake mechanism. One thing that you can do is refer to the equipment manuals that you have on your job site. Make sure that you follow those guidelines and everything should be fine. Well, that's it. You made it through clutches and brakes. If you have any questions after watching this video and reading the textbook, please post them in the Q&A discussion. Thank you very much for watching.